This talk presents experiences in Finland on creating a national cross-domain ontology and linked data infrastructure for digital humanities and using it on the semantic web. I am Eero Hyvönen from Aalto University and University of Helsinki, Helsinki Center for Digital Humanities. First, a few words about the semantic web and linked open data. After that, I will discuss lessons learned in Finland on building a national linked open data infrastructure and how to use it in applications. Semantic web and linked open data. The semantic web is based on a web of linked data, sometimes called as the giant global graph. Based on the data, the web of pages, the pages that we humans see and use, can be created. We chose to use linked open data as the technical basis for our work. There are several reasons for this. By using linked data, everybody's data can be collaboratively enriched by each other's data instead of publishing data in separate data silos. Everybody wins by collaboration. By using linked data, it's possible to create findable, accessible, interoperable and reusable data using the FAIR principles. This means that the value of the data increases. Finally, creating more intelligent applications for the public, curators and researchers is possible. When the machine understands the data, it's possible and more cost efficient to create intelligent applications. The technological basis of the semantic web consists of layers of abstraction based on the layer cake model of W3C. RDF schema and RDF are used for representing data and metadata. On top of that, there is the layer of ontologies that define metadata schemas and concepts that are used in populating those schemas. The semantics of the semantic web are based on logic and proof. And finally, the most upper layer of the cake is called trust. This means that there must be also standards for representing trust of the information that is published on the web. How to build a national linked open data infrastructure. Lessons learned in Finland. Leonardo da Vinci has said, "Learn how to see. Realize that everything connects to everything else." This wisdom is very true regarding both national and pan-European cultural heritage contents and the planned European collaborative cloud for cultural heritage. However, cultural content linkedness gives us two major problems to tackle. The first key problem is that cultural heritage contents are richly interlinked, not only on a national scale, but across the borders of European countries and beyond. We all share common history and cultural background. For example, a book or epic may be the source of inspiration for a symphony, a painting, and is related to biographies of people, cultural sites, objects in museums, and so on. The cultural content includes texts, speeches, images, 2D and 3D models, movies and animations represented in incompatible formats using different national data models and using different natural languages. The second key problem is that cultural heritage content creation is distributed in different kinds of organizations, including not only memory organizations, but also media companies, land survey organizations, communities producing data such as Wikipedias, as linked data clouds, and different citizens participating in citizen science initiatives. When independent parties create content independently from each other, the result is an avalanche of data silos that do not speak with each other. A painful lesson learned in creating pan-European services such as Europeana is that it is very difficult to make the data silos interoperable and reusable. A solution model to address the two previous key problems is depicted in this figure. The idea is to establish a shared data and ontology infrastructure based on linked data. When a content provider creates a piece of content,
using the shared infrastructure, the data is automatically interlinked and enriched by the other data providers' data, and their data by the new piece of content. In this model, everybody can win, both content providers and the end users, by getting access to the enriched interlinked data. The European Cultural Heritage Cloud could be a platform for fostering this work. This image illustrates some essential elements needed for a linked data-based cultural heritage cloud. Shared ontologies and data models are needed as semantic glue that binds the contents together. Datasets and data services enrich the contents by mutual interlinking and for applications created by public organizations and creative industries. The technology is based on standards and best practices of the World Wide Web Consortium and other international standardization bodies. By sharing software tools, unnecessary redundant development work can be avoided. An important part of the model is developing a human infrastructure for the new collaborative model for producing, publishing, and using cultural heritage linked data.
Albert Einstein has said, "Intellectuals solve problems, but geniuses prevent them." This wisdom applies very well to infrastructure building.
A key challenge in the presented model is to create an ontology and ontology service infrastructure. We started to work on this problem in Finland in 2003.
The most important elements of a national ontology infrastructure for digital humanities are various domain ontologies, shared metadata models, and ontology and linked data services online. If we have a closer look at the different ontologies, we can see that they are actually organized in a kind of hierarchical way. We have a very big top ontology, the ISO ontology of general terms by the National Library, and the other ontologies, for example, the AFO ontology for agroforestry and MAO ontology for museum domain, they refine the concepts that are already defined on an upper level in the ISO ontology. These ontologies overlap with each other quite a lot. For example, ISO and TAO share 2000 concepts. And the problem then is how to interlink these ontologies that share so many concepts with each other in a reasonable way.
To disseminate the ontologies of the linked ontology cloud COCO, we created a prototype of a national ontology service called Onki.fi in 2008. In 2014, the National Library of Finland deployed Onki service as Finto.fi service. This is a free service in Finland to be used by API calls and human users. In addition to publishing ontologies as services, we need data services for publishing linked open datasets. For this purpose, we created the Linked Data Finland platform LDF.fi.
Linked data services typically make use of the 5-star linked data model. The idea of this star model is to encourage people to publish their data in a useful way. You get 1 star if you publish your data in whatever format, like in PDF form. You get the 2nd star if you publish your data in some structured form, for example, as an Excel spreadsheet. You get the 3rd star if you use in your structured format some non-proprietary standard. For example, you publish your data as a CSV file instead of as an Excel file. Then comes the linked data part, actually. You get the 4th star if you are using IRI or URI identifiers in your data and interlink it internally. And then you get the 5th star if you provide the links not only within your own dataset, but also to other datasets in order to enrich those and get more information also to your own dataset.
Linked data publications are typically evaluated by using the 5-star model of Tim Berners-Lee. This comes from the hotel world. The idea of Linked Data Finland is to extend the 5-star model to a 7-star model, as there are hotels of 7 stars in the world. The idea is to enhance reusability and data quality. You get the 6th star if you provide your data with the schema and documentation so that people can understand and reuse your data easily. And you get the 7th star if you validate your data and denote its provenance so that people can trust the quality of your data.
This figure illustrates the landing page of the Linked Data Finland platform. On the left, you have different options to browse different services. For example, the datasets link takes you to a list of different datasets available in the service. Each dataset in the system has a home page that is automatically generated from a metadata description of the dataset. For example, here you can see the home page of a Vorsampo dataset, the data that is used for creating the Vorsampo application.
Some experiences and lessons learned in creating national data services. The Linked Data Finland platform makes it very easy to publish data. The services are generated automatically from service description metadata description. Reusing services and support functions is very cost efficient, I think, because unnecessary re-implementations can be avoided in this way. The platform turned out to be very useful also for building human infrastructure. We have used it in hackathons, in educational university courses, for example. The basic services in a system like Linked Data Finland can be run with little maintenance. However, technical expertise is of course needed there on semantic web technologies. A system like Linked Data Finland must be sustainable. It is now part of National Research Infrastructure Roadmap of the Academy of Finland, so this is a kind of first step forward. And we are lucky that the servers are provided for free for universities by the CSC company owned by the Ministry of Education and Culture. An issue that is still a challenge is how to keep the data and services up to date. For example, when the data changes somewhere or an ontology changes somewhere, how is that change propagated to all other services and datasets that use that data?
How to use the infrastructure for applications, Sampo model and Sampo series of systems. During the last 10 years, we have developed and used the Sampo model in Finland for creating a series of linked open data services and semantic portals on top of them. The name Sampo refers to the mythical artifact of the Finnish epic Kalevala that gives its owner riches and good fortune. It is usually seen as a metaphor of amazing ancient technology. The Sampo systems have in some cases had millions of users on the web, suggesting feasibility of the proposed approach. As linked data semantics are domain agnostic, the model can be used in various application domains. For example, Culture Sampo is about artifacts in museums, interlinked with a variety of tangible and intangible cultural heritage, including the epic Kalevala. Book Sampo is about Finnish fiction literature. War Sampo is about Second World War history. Biography Sampo is about biographies, and Name Sampo about historical places in Finland. Sampo is about medieval manuscripts, and Find Sampo about archaeological finds. Letter Sampo is about epistolary data, Parliament Sampo about parliamentary discussions and networks as politicians, and Law Sampo about Finnish legislation and case law.
As a practical example of using a Sampo portal and a linked open data service, I will show a video about Letter Sampo, historical letters on the semantic web.
This video introduces the Letter Sampo project at the Aalto University and Helsinki Center for Digital Humanities Helsinki. We are developing a framework and a demonstrator for publishing and analyzing historical epistolary data in digital humanities based on semantic web technologies. This new project in Finland was inspired by our earlier collaborations with the Pan-European EU Cost Action Reassembling the Republic of Letters and the University of Oxford. related to historical letters sent from the 16th to 19th century in Europe and beyond. Letters are always sent from a place to another and are therefore scattered in different archives in different countries, written in different languages, harmonizing the metadata from separate data silos and aggregating the data into a semantically interoperable global service for digital humanities analyses makes a nice use case for the SAMPO model and SAMPO UI framework, developed at the Semantic Computing Research Group. The SAMPO model includes a collaborative business model for collaborative data publishing in a shared linked data service, the idea of accessing the data from multiple perspectives, the idea of integrating the service seamlessly with data analytic tools for research, and finally, a model for addressing research questions in 2 steps, where faceted search is first used for filtering out data of interest, and data analysis and visualizations are then applied to it. We next illustrate this idea by showing examples on analyzing letter data by using the Letter SAMPO demonstrator. This is the main entry page for the Letter SAMPO user interface. The application consists of 3 perspectives to the underlying data: the actors, the letters, and the places. The underlying dataset in this example contains information about a total of 34,000 actors. By actor we mean an individual person or group of people like universities or religious organizations. In the faceted search we can filter or search specific actors by their name, gender, or times of birth or death, or groups of actors for prosopographical research. For example, we can search for the mathematician Gottfried Wilhelm Leibniz. On the result page we will see him among the other matches. The result table shows his years of birth and death, and the amount of the letters involved, based on the underlying metadata. On the person landing page we will have even more information about him and his correspondences. In addition to showing his basic biographical information, the page contains fields for his alternative names and vocations. There is a list of all the other actors with whom he has been in contact. It should be emphasized that any visualization or data analysis in a system like Letter SAMPO is an analysis of the underlying dataset, not of the real world. Any conclusions drawn from the analysis need source criticism and understanding the limitations of the data. For example, in this example there are 149 letters of Leibniz and the data misses lots of letters. Leibniz was a very active writer with some 15,000 letters and 1,100 correspondence, so in this case only 1% of those are available in the demonstrational dataset. In spite of this, analyzing an incomplete letter collection by distant reading can give novel insights to the researcher and collection manager, and suggest topics of interest for further close reading. The first person on the list is Christian Huygens, with whom he has sent 70 letters. As far as the data can tell us in this case, there are also detailed lists of all letters sent or received by him. The last result on this page shows a list of places he has been active and based on data about sending or receiving letters. The next tab, Network of Letters, shows a visualization of actors' egocentric network. The link width between 2 actors indicates the amount of mutual correspondence. The wider the link, the more letters has been sent between the 2 actors. We can for instance spot that Leibniz sent 39 letters to Christian Huygens, while Henry Oldenburg sent more than 200 letters to Huygens. Again, this analysis is based on data about only a fraction of Leibniz known letters. The next tab illustrates the number of letters on a timeline, where we can observe that the data is based on letters from 2 periods, the first one in the 1670s, and the second in the 1690s. This could indicate the collection manager that letters in between may be missing. The letter perspective page has a similar faceted search application as the actor page. Here we can browse and filter the data of 162,000 letters by their sender, receiver, date, language, subject, or data source. The second tab on the letter page visualizes the letter routes on a map application. Currently we are viewing the routes of letters sent from Paris. The third tab on the letter page demonstrates the amount of correspondences on a timeline. From this curve can be seen that the data is distributed from 16th to 19th century, with the majority of letters in the 17th century. In addition to the ready-to-use data views in LetterSampo, the underlying SPARQL endpoint can be used easily for further data analyses using, for example, Python scripting in Google Columns. This data table shows the most active mathematicians in the data set, filtered out from the data. The left column shows the actors ranked by the number of letters sent. In the middle column, ranking is based by the number of received letters, and on the right by the total amount of letters. The blue text color indicates that the actor has written more letters than what he has received. This is a visualization of the top writers between the years 1620 and 1770, and the ranking of the author is depicted on the y-axis, so that the highest ranking actor appears on the top of the diagram. Based on the underlying collection data, in the 1620s and 1630s Marin Mersenne was at the highest rank. Christian Huygens was among the top writers during the years 1650 to 1690s. Isaac Newton has been an active writer in the late 17th and early 18th century. And finally we have Leonard Euler, who's been the top writer during 4 decades from 1730s to 1760s. Thank you all for watching this video. More information about the LetterSampo project is available at the web page of the Semantic Computing Research Group.
The Sampo model and portals aim at making a paradigm change in publishing and using cultural heritage content on the web. The contents are published as linked data and also integrated seamlessly with intelligent tools for data analysis. In our vision, artificial intelligence should help the user in solving research problems and also in finding new ones using creative AI methods.
The work presented on developing Sampo applications demonstrates that domain-agnostic semantic web standards and practices can be applied in virtually all domains. A national semantic web infrastructure is the key for cost-efficient application development. It is possible to create systems that are popular in use and have lots of novel features. Reusable software tools such as the Sampo UI have been quite essential in developing the systems. Sustainability of the applications remain a challenge as the technologies are still new to data owners. The line of research suggests a paradigm change in web publishing. New avenues to the future are now open.
But the launch is not free. More collaboration is needed between organizations, and this of course complicates work. Integration of semantic portals and data services with legacy systems is a challenge in many places. Manual annotations are costly and may not scale up, but on the other hand, if we are using automatic annotation and linking, this lowers data quality. In general, using systems like Sampo's, one needs much more source criticism and data literacy. What the data actually is and means is not always clear. Big data quality issues arise also, like completeness of data, skewness of data, and different errors made in the data transformation processes.
Thank you for listening. More information about the work presented can be found on the home pages of the Semantic Computing Research Group.